Well, good afternoon. It's a pleasure to introduce Professor Marek Karliner, a person who devoted the most of his life to the study of QCD, hadron structure, and since about 15 years, though all these quite exotic and for me confusing states, including several heavy bound states, including several heavy quarks. Professor Karliner has quite a remarkable series of prizes and worldwide collaboration with Stanford Lab, with Cambridge, with CERN, and quite a huge score of prizes. I would like also to underline one of your first prizes by the Italian government. As a remarkable student, it's quite nice to know. Okay, well, I cut it short and I let him introduce us to this sociological talk. Thank you.
Thank you very much. È un gran piacere essere qui a Padova, la prima volta per me. I will switch to English. I like speaking Italian, but I can't speak about physics in Italian. So it's a real pleasure to be here, and today I would like to tell you about some new and interesting developments having to do with unusual combinations of quarks. Maybe we switch off this. Oh, okay, good. So I call it the social life of quarks, and in the following sense: who with whom? For how long? Is it a one-night stand? Or is it till death us part? So the outline is the following. Quarks are fundamental building blocks of protons, neutrons, and all hadrons. To paraphrase Orwell, all quarks are equal, but heavy quarks are more equal than others. And recently, we have observed new combinations of light and heavy quarks, including so-called exotic quarks, and I will explain this concept. And moreover, there are several kinds of these exotic combinations. One is called hadronic molecules. Most recently, a discovery made by LHCb at CERN, something called the pentaquark. I will also mention a prediction and discovery of a doubly charmed baryon, a baryon which contains two charmed quarks. I will discuss the prediction, which is now considered quite robust, for a tetraquark, a state containing two quarks and two antiquarks, which is stable. It cannot decay through strong interactions. I will then discuss an amusing result of the strong forces between quarks. There is an analog of nuclear fusion with quarks coming in place of nucleons. And I will discuss some possible applications of this in the dark matter sector. So as you all know, there are several layers of matter, starting with crystals, molecules, atoms, nuclei, protons, and protons are built out of quarks. And as far as we know, quarks are point-like. The most astonishing experimental fact about quarks, and in general about fermions, is the huge hierarchy of their masses. Quark masses, the lightest ones are a few MeV, and the heaviest one is the top quark, which is about 170 GeV. And this is many, many orders of magnitude, and nobody in the world has any idea why we have such a huge span of masses. This is one of probably the most interesting open question in the world of quarks. I will not provide an answer, of course, today, but this is something which is worth keeping in mind. And if you look at the span of fermion masses, starting with neutrinos all the way to the top quark, then this really is mind-boggling, 14 orders of magnitude in mass. What is the mechanism which generates such a huge hierarchy of masses? We don't know, and of course there are many speculations. It's a totally open question. So the classification of states containing quarks has a history which is somewhat parallel to the history of periodic table of elements. In 1961, an Israeli physicist, Yuval Ne'eman and Mary Gell-Mann at the same time in Caltech, found an organizing principle analogous to the Mendeleev table, which explained why certain combinations, why certain hadrons are seen and others are not seen. It enabled them to predict which ones are missing. And one of them was quickly discovered, the omega minus. This convinced everybody that this scheme had a good theoretical basis. A few years later, Gell-Mann and also Zweig explained this SU3 pattern by postulating that all then known hadrons are built out of three quarks, U, D, and S, and basically you have all the combinations. And if you consider the possible combinations of such three quarks, you have all the baryons that you observe in nature, and you can also have combinations of a quark and an antiquark. So, for example, a proton is two U quarks and a D quark. A neutron is two D quarks and a U quark. A pion is a U and an anti-D. A positive pion and negative pion is an anti-U and a D. Baryons are composed out of three quarks. Mesons, such as pions, are composed out of a quark and an antiquark. Now, quarks carry, in addition to the electric charge of U is 2/3 and of D is -1/3. They carry also another charge called the color charge. And the rule is that the only combinations which are allowed are those combinations of quarks in which the total color charge vanishes. This color charge is called color because there are three basic types of this charge, and when you combine them together, you get something which is chargeless, which is analogous to combining three basic colors to get a white color. Okay, and this interaction of these color charges is very, very strong and has the most peculiar property, which is completely different from anything we have seen before, and that is the fact that the potential raises very rapidly, raises linearly with distance. The force is constant. This is something that we have never seen before. We now know this for a fact from a variety of sources, that when you take a color charge and a color anti-charge and you pull them apart, the force between them is constant. In the 70s, people discovered bound states of a charm and anti-charm and were able to reproduce the spectrum of these bound states called charmonia using Schrödinger equation. And this was a revolution. suddenly we are able to predict with very high precision properties of all known hadrons. So the potential between two heavy quarks has two components. One is like in electrodynamics. It's a Coulomb-like potential, except that the coupling depends on the distance, so-called running coupling, plus a term which is linear in the distance. At small distances, the linear term is unimportant, and you are dominated by the Coulomb behavior. At large distances, the Coulomb term becomes unimportant, and the potential raises linearly. We now have been able to perform simulations which show what happens when you take two color charges apart, a charge and an anti-charge, or when you take three color charges and make them further and further away from each other. And you have here some simulations which show what happens. So basically, a flux tube is formed. Unlike in electrodynamics, where the flux spreads over all space, here the flux is confined to a relatively narrow tube, and this is the reason why the force between quark and an antiquark is constant and the potential raises linearly. So in principle, one could think that you pull them apart further and further away, and the potential energy grows without limit. But this is not what happens. This would only be true in classical theory. In a quantum theory, when you take the two color charges apart from each other at a sufficiently large distance, the energy stored in the field becomes so large that you can utilize this energy to create a new quark-antiquark pair, and this new pair neutralizes the two original charges. We call it the string breaking. So here you have a simulation of such a breaking of the string. This is the energy density or the action density. See, it grows and then suddenly it goes down. The string breaks. So standard hadrons that we have known for a very long time are either mesons, a quark and antiquark, or three quarks. Exotic hadrons are other kinds of combinations which are also without color. The total color is zero, but you can obtain it in non-trivial ways. For example, by combining two quarks and two antiquarks, or by combining four quarks and one antiquark. This is called the tetraquark. This is called the pentaquark. So the people who invented quarks, Gell-Mann and Zweig, knew about this possibility already in 1964. This is from the original papers by Gell-Mann and Zweig. But what people did not understand, that there is a difference between the possibility of having such combinations because they satisfy the criterion that they are colorless, and having them stable dynamically. And for many years, people looked for exotics made only out of light quarks and never found anything. But recently, when people started to run experiments with heavy enough quarks and large cross-sections, we have seen clear evidence of such exotics containing both light and heavy quarks. And this is the main focus of my talk today. So the big questions about exotic hadrons, I remind you, exotics are those which are not either quark-antiquark or three quarks. The big questions about such exotic hadrons is, first of all, do they exist? This is an experimental question, or if we understand the theory well enough, we should be able to predict it and then test it experimentally. If they do exist, which combinations are stable dynamically? what is their internal structure? How are the quarks organized inside? And finally, and this is a very important question, where is the best place to look for such combinations experimentally? After all, physics is an experimental science. Nobody will believe us unless we see these things in an experiment. So, the reason we look at hadrons with heavy quarks is that hadrons with heavy quarks are much simpler. And they are much simpler because heavy quarks barely move. They have very low kinetic energy. They have small interaction, which depends on spin. And this, at the time, some years ago, was a key to an accurate prediction of masses of baryons containing one big quark. So you see, this is, in blue is the prediction, and in red and green are the measured values of the mass. And this was done in collaboration with Boaz Kerentzur, who was a grad student of mine, with the late Harry Lipkin, and with John Rosner, who is at the University of Chicago. And this gave us encouragement to apply the same methods to states containing two heavy quarks. And in fact, in 2008, with Harry Lipkin, we predicted that an anomaly observed in the data of an experiment called Bell in Japan, they measured some decay rate which was 2 orders of magnitude too big. And we explained this by postulating that this rate is enhanced by an exotic combination of anti-B and a B bar B, and a U and a D bar tetraquark. And we told them where to look for it. It took 3 years, and then indeed they found it. And in Japan, in Bell, and another experiment called BESS3 in China found the analog of these resonances containing charm quarks. So we now know that they contain a charm and anti-charm. Something funny is going on. Where's the microphone? Let's see. Okay, let's hope. The pointer. Ah, okay, maybe. So I'll keep the pointer in my left hand. Yeah, but I also need this pointer to switch slides, so now let's, okay. So in Bell and BESS experiment in China, they discover states which decay into a bound state of a B bar and a B and a pion, or C bar and a C and a pion. That's a clear indication that these are exotic states containing 2 quarks and 2 antiquarks. And there is a whole family of such states, and they share something very unusual. There are 5 states like this, and the property that they share is the following. All the 5 states have a mass which is very close to mass of 2 mesons, so-called heavy light mesons, D bar D, B bar B, and so on. And they decay into a meson which is a combination of 2 heavy quarks and a meson which is a combination of 2 light quarks, like J and a pion, or upsilon and a pion, and they have lots of energy for this decay. Hundreds of MeV, in one case 1,000 MeV. Yet, they have an exceedingly long lifetime or narrow width by standards of hadronic physics. This is very unusual, because usually when a state has lots of energy available for decay, no, this is, I haven't pressed anything, so I don't know. Such a state, maybe the telephone, okay. Let's put the telephone here. Could be the telephone. So, it's clear that something non-trivial is going on. You know, a typical width of a hadronic state, which has hundreds of MeV of available phase space, should be at least 100 MeV. These things are very, very narrow. So clearly, there is some obstruction which prevents them from this decay. And that's interesting. When something unusual happens, it's always interesting. Another interesting thing is what we don't see. We see combinations of a meson with spin 0 and a meson with spin 1, or two mesons with spin 1, a meson and an antimeson. We never see such states at the threshold of two mesons with spin 0, two pseudoscalars. This is very puzzling. And as you will see, this is the key to understanding what these states are. Okay, this is a graphical display, what these states look like. This is the threshold of two B bar, B star, spin 0, spin 1, spin 1, spin 1, and this is the same thing in the charm sector. So we postulated, and I will try to convince you why we think this is true, that what these things are the analogues of deuteron. So what is a deuteron? A deuteron is a bound state of proton and neutron. In this bound state, the proton and the neutron retain their separate identities, and they feel a weak binding potential. The binding energy is just about 2 MeV versus mass of 2 GeV. So it's barely bound. And they bind by exchanging mesons, pions and other light mesons. So what we think is going on here is an almost exact analog of this process, where you have one meson containing a charm quark and an anti-U, another containing an anti-charm and a U, and they are very heavy, so they have a little kinetic energy, and they form the analog of a deuteron. We call them hadronic molecules. Now, in principle, you can take these 4 quarks and package them in a different way. You can put all of them in a small amount of space, which will be, and the arrangement will be very different from the deuteron. In the deuteron, the quarks inside the proton and the quarks inside the neutron don't talk to each other directly. But if you package them into very small space, that would be a different story. This we call a tightly bound tetraquark. This is a hadronic molecule, and this is a tightly bound tetraquark. To make a somewhat more everyday example, consider that you have 2 couples of friends, a boy and a girl and another boy and a girl, and they go on a trip together, and then they need to decide, it's a long trip, 2 days, so they need to decide how they are going to spend the night. And there are 2 possibilities. They either rent 2 rooms or they rent 1 room. It's a very different arrangement. Okay, so please keep in mind, this is 2 separate rooms. This is 1 room. Very, very drastically different. Okay, so we need to look at some experimental facts to help us decide which possibility was chosen by nature. So, for example, there is this state called ZB10610, which can decay either to 2 heavy mesons, each containing 1 heavy quark and 1 light quark, which we think that's the molecule. These are the constituents of a molecule. Or they can rearrange in such a way that the 2 heavy quarks bind together into something called upsilon, and the 2 light quarks, a quark-antiquark, bind together. They form a pion. Now, the energy available for the process in the numerator is just a few MeV. The energy available for the process in the denominator is 1,000 MeV. So naively, you would expect that the process in the denominator is dominant. But in fact, experimentally, it's the other way around. The strength, the probability for the process in the numerator is about 100 times bigger than the process in the denominator. Now, this is shocking. Okay, so clearly, this state doesn't want to go to this final rearrangement of 2 heavies and 2 lights. So this is like swapping, okay? This is just the 2 couples go, they separate ways, and this is exchanging partners, a much more difficult process. And there are examples less dramatic from other processes. So we have 4 pieces of experimental evidence supporting the molecular interpretation of these states. First of all, the masses and the quantum numbers of these states are as if they are bound states in S-wave of the 2 hadrons. They have a very narrow width despite a very large phase space. The fall apart mode has a much higher probability than the rearrangement mode. And finally, this thing that I mentioned at the beginning, this fact that we never see a bound state of 2 scalars, or rather 2 pseudoscalars. So why is this relevant? It is relevant because you can show that the type of forces that are utilized in these hadronic molecules can never bind together 2 pseudoscalars. It's just forbidden by conservation of spin and parity. So that provides a natural explanation why you cannot have such a state. So you then try to ask yourself, okay, what are the necessary conditions for having such a hadronic molecule, the analog of the deuteron? And first of all, both hadrons must be heavy because the kinetic energy is inversely proportional to the reduced mass. They must couple to pions. They must have spin and parity, which allow binding by exchange of pions. And they need to be narrow. And then you realize something interesting. This binding mechanism can apply not just to 2 mesons, it can also apply to a meson and a baryon or 2 baryons. We know it applies to 2 baryons because we have the deuteron. So it is easy, once you make that realization, it is easy to write down a list of states which should be observed, which have this property. And in this list, we immediately see states which have been observed already, these 2 and these 2, but also you should see a bound state of a D star and a B star, but you also should see a bound state of a baryon and a meson, a heavy baryon and a heavy meson, each containing 1 heavy quark, and many other states. So what are the properties of the lightest bound state hadronic molecule containing a baryon and a meson? It should have a mass which is close to the threshold, slightly below 4460 MeV. It can decay into a proton and J psi, and we predicted that if it has isospin 1/2, it should have spin 3/2. And even though, so we predicted it has a very large phase space available, it should have a narrow width, a few tenths of MeV. The quark content of the state is C bar C UUD. And it's a molecule. It's not a tightly bound pentaquark, because if it was a tightly bound pentaquark, it would be very easy for it to decay. And I will explain this. This is a crucial point. So this is the list of these states. This is the decay mode, the mass. Below that, slightly below this number. And we were very lucky because we put this paper on the web in June 2015. And in July 2015, LHCb announced the discovery of precisely such state. And both papers were published in Phys. Letter, the prediction and the observation. So what did they see? When you study resonances, there is a very nice graphical technique. You plot the amplitude parameterized by the energy. You plot the complex amplitude, you plot the real part, the imaginary part versus the real part of the amplitude, parameterized by the energy. And if you have a Breit-Wigner, a perfect Breit-Wigner will give you a perfect circle going counterclockwise. So you see almost a textbook example. They saw two resonances. This one is very, very beautiful. It has a mass just 10 MeV below the threshold, as predicted, very narrow width. This guy that they observed is a very wide state, less statistically significant. It's not clear what it is. The point is that if we are right, that this indeed is a hadronic molecule consisting of a charm baryon and a charm meson, loosely bound, then it's just the first of many such heavy deuterons. It's like having a glimpse at the first entry in the second layer of periodic table. Because what these things are, really, they are the analogues of nuclei, light nuclei. So again, the issue of width, I want to stress it again. So let's consider two possibilities. The final state is a charm quark and anti-charm quark and proton, UUD. Who has a better chance, for whom it is easier to decay into this final state? If you put all 5 quarks into the same bag, you know, everybody in the same room, then splitting is very easy, because all that needs to happen is that the charm quark and the anti-charm quark perform an act of secession. They just go away. They couple to each other and they form a bound state, and they leave the 3 light quarks behind. But if the initial state is one where you have 1 heavy quark in a baryon and 1 heavy antiquark in a meson, and these 2 objects are fairly far from each other, then it's quite difficult to make the exchange, because in order to form a CC bar, these 2 things must first get close together. And the wave function is such that the probability is small. It's like the probability in hydrogen atom of having the electron inside the nucleus, inside the proton. There is a probability, but it's small. Another way to put it is, if you have a commuting marriage, it's somewhat difficult to make children because you need to meet, and that requires an effort. So this is a natural mechanism explaining the very narrow width of the state despite having a lot of phase space. Okay, you can repeat this exercise with perhaps with baryons. I won't dwell on this, but now I want to switch gears and talk to you about states which are not exotic, but which had never been seen until last summer. Summer of 2017. From QCD, it's absolutely clear that such things must exist. Two heavy quarks, one light quark. There is nothing exotic about them, but the challenge was to predict their masses and to convince the experimental community that the cross-section is large enough so they can be observed at CERN in the LHCb experiment. We managed to do that, both. We wrote a paper in 2014 pointing out that LHCb sees thousands of mesons containing a heavy B quark and a heavy anti-charm quark. And it turns out that the bottleneck in producing such a state is exactly analogous to the bottleneck in producing baryons containing two heavy quarks. It's like the argument, we know empirically that in places where you find silver, you also find gold, because the geological processes which form them are similar. So what we told LHCb is, look, you already found the silver. You know you can do it. You have the cross-section. It's just a matter of putting in the effort. And they worked very hard for 3 years. And as you will see, they found it. And so, first of all, you need to predict the masses of such things. And the masses are predicted using the same toolbox that was used to predict masses of baryons containing one heavy quark. And so in 2014, we predicted that the lightest such baryon, let me put it here, so two charm quarks and a U quark, it is called psi, for historical reasons, it's called psi CC. It has charge plus plus, and the theoretically predicted mass m psi cc 3627 plus minus 12 MeV. I won't go too much into details how it was done. And then in July 2017, they discovered this thing with a mass of 3,621 plus minus 1 MeV. Which makes it very likely that we got it correct. That not just the number, but the mechanism. So what goes into this calculation? It's not a calculation from first principles. Nobody knows how to do this analytically. People know how to do such calculations numerically on the lattice. But analytically, what the best you can do is to do a phenomenological approach. You identified the quark model, you identify the effective degrees of freedom and their interactions, extract the parameters of the model from other experiments, and then use them to make predictions. And what are the crucial ingredients? The masses of the heavy quarks that we know, the potential between heavy quarks and light quarks that we know, the masses of light quarks that we know. One thing we didn't know and nobody knew is the interaction between heavy quarks themselves. That is why there was a stumbling block, and for a long time nobody was able to do this calculation. So when you are stuck, you make an educated guess. And the educated guess that we made turned out to be correct. You can show that in the limit where the coupling is weak, the potential between two heavy quarks is exactly 1/2 of the potential between a heavy quark and a heavy antiquark. But the potential between a heavy quark and a heavy antiquark, you know from experiment. So we knew that number, modulo the assumption. And it took us a while to understand why this assumption is in fact correct, also in bound state, not just in scattering. So once you make that assumption, everything else is easy, and you just have, this is your bookkeeping. This is how you get the 36, 27 plus minus 12. The crucial ingredient is the very large binding energy, almost 130 MeV between the two charm quarks. And you make your error estimate and so on. This turned out to be absolutely essential for the next step. So we have this prediction which has been verified experimentally. We have predictions for other states which will be observed by LHCb with time. They need more statistics, but they will do it. This is eyes view of CERN, and the LHCb experiment is here. Those of you who have not been to CERN, I think it's worth a trip. This is probably the largest experimental facility in the world, 28 kilometers in circumference, 100 to 200 meters below the ground. This is what the experiment looks like. And this is a schematic plot of this baryon containing two charm quarks and one light quark. And you can predict their lifetimes. They would decay through weak decays. This is fairly standard. So now comes the next step, which is not yet verified experimentally, but has been verified after we wrote our paper. 3 different groups did the calculation by different means, and we all agree now that there is a deeply bound 4-quark state. So the same theoretical toolbox that led to the accurate prediction of the Xi-CC mass now predicts a stable, deeply bound tetraquark containing 2 B quarks, 1 anti-U and 1 anti-D, more than 200 MeV below 2 meson threshold. This is the first manifestly exotic stable hadron, stable in the sense that it cannot decay through strong interactions. It can decay by weak decays, but that's like 10 orders of magnitude in lifetime. So it's infinity from the point of view of strong interactions. So this is a Physrev letters that was published in November last year as editor's suggestion, and we predict the mass. And so what's going on? How does it work? First of all, what's the configuration? The configuration is that you have these 2 B quarks coupled very tightly together. And you have two light antiquarks also coupled tightly. And it's closely analogous to a baryon, because when you couple two antiquarks to each other, they form a color triplet, just like a quark. Now, why is it bound? What's the trick? The point is that when you have two heavy quarks, they essentially sit on top of each other. Just like when you take the hydrogen atom and you replace the electron by a muon, the radius shrinks by a factor 200 because the radius is inversely proportional to the mass. This inverse proportionality is exact for Coulomb potential. This potential is not exactly Coulomb, so it will not be exactly inversely proportional to mass, but a system of two big quarks is very, very small. It's about 1/5 of a Fermi. Now, in the beginning of this talk, I showed you the quark-quark potential. So let's have a look, because now it becomes essential. Okay, all right, it doesn't move. Okay, here it is. So we have this potential, which is a linear term and a Coulomb term. When the radius, the distance is very small, this term is negligible. Now, if r is very small, then 1/r is a very large number. Even though alpha is a small coupling at small distance, it's small logarithmically, whereas 1/r is big power-like. So 1/r wins, and you get a huge binding energy. And we know this binding energy because, again, just like in the case of the doubly charmed baryon, we can estimate the binding energy from the bound state of bottom and antibottom. This we have in experiment. You just take the binding energy of B and anti-B divided by 2, and you get this huge binding energy, minus 280 MeV. So now I want to explain why this is stable, okay? Can I have the light on for a moment? Is there somebody who knows how to operate the light? Okay. So this is our tetraquark. U bar, D bar, BBU, BB, U bar, D bar. And I want to compare the binding energy of this configuration versus two mesons, B U bar and B D bar. So what's going on? In here, you have the two big quarks next to each other, interacting through this Coulomb potential and having a huge binding energy. When it dissociates into two mesons, this B doesn't talk to this B. They are completely independent. So you lose this 280 MeV. This is the essential mechanism which causes the mass of this object to be 200 MeV below this mass. So 215 actually in our calculation, below two mesons. Now this is the lightest non-exotic configuration containing these four quarks. So since this is the lightest non-exotic channel, you are stuck in an exotic configuration. There is nowhere you can decay to. The only way this can decay is by weak decay, but that takes a very long time on a hadronic scale. Okay? Can we switch it off, please? Okay, thank you. All right. So this is, again, our mass budget. This is the mass. This is our prediction. And after we published our paper, several other groups predicted very similar results. We differ by 20, 30, 50 MeV, but we all agree that they are deeply bound. And the most interesting fact is, the most interesting fact is LHCb says they will be able to observe it. They just need more time to have enough statistics. But observing such a state, once it is produced in LHCb, is doable. So this is very exciting. We have a highly non-trivial prediction which can be tested experimentally. Nowadays in particle physics, this is a great luxury. You make a prediction and somebody can test it in your lifetime. Okay, so you can try to do this with one big quark and one charm quark. Now what do you expect? The heavier the quarks, the closer they get to each other, the bigger the binding energy. So if you have one B and one charm, it's not going to be bound as much. And if you have two charms, it's going to be bound even less. So you do the calculation, and this is what you get. This is two B quarks and two light antiquarks. This is a B and a C and two light antiquarks, a little bit below threshold. And this is two charm quarks. In our calculation, it comes out a little bit above threshold, but this is our error bar, so we really don't know. But in any case, even if it's above threshold, it will be very narrow because it has a tiny phase space for decay. Now, you can produce these things almost as easy as you produce doubly heavy baryons. And this is very important because LHCb has proven that it can produce doubly heavy baryons. So it's just a question of time until they will observe this doubly bottom. First, they need to observe doubly bottom baryon. Once they observe, which is non-exotic, it's just something we know it's there. But once they observe the doubly bottom baryon, BBU or BBD, we know that the cross-section for making this exotic combination is going to be maybe a factor of 10 less. So it's not very difficult. Once you have enough statistics to see the non-exotic baryon, you should see also the highly exotic tetraquark. Okay. So, moreover, since they have observed the doubly charmed baryon, they probably have by now enough statistics to see the doubly charmed tetraquark, which is above threshold. We are waiting eagerly to hear if they actually see it. It's being searched for as we speak. Okay, you can estimate the lifetime. A typical lifetime is a few hundred femtoseconds. A typical weak interaction lifetime, 10 to the minus 13 seconds. And the decay channels are just the standard weak interaction decay channels. There is nothing exotic there. And it's important to list those decay channels because you tell the experiments where to look for such a thing. So to summarize, we have the first stable, deeply bound tetraquark. It's unusual in one more thing. The spin is going to be 1. You know, Neutron has spin 1. That's also unusual. Usually ground state in quantum mechanics, a bound state of some object is spin 0. But there is a very good reason why this object has spin 1. The reason is that two identical fermions, two identical quarks in such a configuration must couple to spin 1. They cannot couple to spin 0 because of Fermi statistics. And the lightest configuration of two different quarks, the U bar and D bar, has spin 0. So the total is going to be spin 1 and positive parity. Color? What do you mean? Exactly. So you couple two heavy quarks to a color antitriplet, which is antisymmetric in color. The total thing has to be antisymmetric. So it must be symmetric in spin. It's already antisymmetric in color. It's, by construction, symmetric in flavor. You don't want to excite a radial orbital. So it must be symmetric in spin. That's precisely the point. So it must be spin 1. And the lightest configuration of two different quarks is spin 0. So you have spin 1 diquark and a spin 0 diquark, which couple to spin 1. So there is a robust prediction that this state has spin 1 positive parity, which is interesting. Okay, and we have the other guys, the BC and the CC. We more or less know where they are. And, okay, I'm going to skip this because time is running short. I also want to say that there could be narrow states containing 4 heavy quarks. They are probably not below threshold, but they could be narrow and could be seen in decay into 4 leptons. CMS might have actually seen something like that. And now I want to spend the last few minutes discussing something which has made a lot of headlines, but it's luckily a purely theoretical exercise, almost purely theoretical exercise. So it's quark-level analog of nuclear fusion with doubly heavy baryons. So first, please allow me to remind you how nuclear fusion works. The simplest canonical example of nuclear fusion is the fusion of deuterium with tritium to give you helium and a free neutron. Deuterium is a proton and a neutron. Tritium is 2 neutrons and a proton. You rearrange them. And the key to producing energy by fusion is the fact that helium-4 nucleus is tightly bound. So basically, the source of energy in nuclear fusion is more efficient repackaging of nucleons. That's all. But now we know we can package quarks more efficiently. Okay? So we can repeat this logic exactly. We can now take, so these are typical energies released in nuclear fusion, ranging from 3 MeV to almost 20 MeV, depending on the particular reaction. Now we can do exactly the same with quarks. Consider a baryon containing 1 heavy quark and 2 light ones, and another such baryon. And you repackage them into 1 baryon containing 2 heavy quarks. This is the analog of helium-4, and 1 baryon containing only light quarks. It turns out, this is now numbers taken from experiment. We know all the masses, so we can calculate how much energy will be released in this. We know the mass of these lambda C baryons. We know this has been measured last summer. 12 MeV will be released, which is the same order of magnitude as the energy released in ordinary nuclear fusion. But if instead of doing this with charm quarks, we do it with bottom quarks, then we know the packaging is much more efficient because the big quarks are heavier, they sit on top of each other, and it turns out that the amount of energy released is dramatically bigger. It's 138 MeV. This is a prediction, but a robust one, which is based on things we know, which is 7 or 8 times more than in ordinary nuclear fusion. So once you write down these numbers, you get scared. What have we done? Okay. And luckily, this is totally useless. You cannot build a bomb. The reason you cannot build a bomb is that in order to build a bomb, you need two things. You need a highly exothermic reaction, which releases a lot of energy, and that you have. But you need to multiply this reaction by an Avogadro number of cases, a chain reaction. But the reactants are highly unstable. Heavy quarks decay in 10 to the minus 13 seconds. So you cannot store the reactants for the bomb. And luckily, nature has made sure you cannot build a device which releases 7 or 8 times more energy than a hydrogen bomb. But nevertheless, okay, this is a graphic comparing ordinary fusion with quark-level fusion. This graphic is taken from an editorial published by Nature together with our paper. They had very good graphic artists, much better than we did. And this is a plot showing how much energy is released depending on which quark combination you take. So if you take 2 big quarks, you release 130-something MeV. With 2 charm quarks, you release 12. With bottom and charm somewhere in the middle. And with 2 strange quarks, you have to invest energy. And it's perfectly logical because binding depends on the mass of the quarks. So one possible place where such things might be perhaps tested experimentally is when you consider hypernuclei, which are nuclei where you replace one of the baryons with a strange baryon. And people in Japan are doing experiments with doubly strange hypernuclei. So you can think about, instead of doubly strange, doubly bottom. And you have a prediction that they will be abnormally light because of this large binding energy. So maybe this can be done. And it's a universal phenomenon. Heavy fermions in fundamental representation of the gauge group, the binding increases monotonically with the fermion mass. This might be relevant, if not for our world, where heavy quarks are unstable, luckily. But people who talk about dark matter sector, for important reasons, consider situations where the analog of big quark are stable. They don't decay through weak interactions. In the dark sector, such a very powerful, highly exothermic fusion mechanism might be possible. So this is now at the level of something that people are working on theoretically. We don't know, but it's nevertheless interesting. So let me summarize. We have narrow exotics containing one heavy and one heavy quark and one heavy antiquark. They are molecules. The most conspicuous among them is the so-called LHCb pentaquark. And there should be many more such objects with bottom and charm and so on. The doubly charm baryon was found exactly where predicted. And there should be more such objects, doubly bottom charm, and so on. We predict a stable, strongly bound, doubly bottom tetraquark. There could be narrow, all heavy tetraquarks. And finally, there is an amusing theoretical observation that ordinary nuclear fusion has an analog with heavy quarks. So there is an exciting new spectroscopy awaiting discovery, and I would like to stop here. Thank you.
Thank you for this very charming seminar. Are there any questions? Yes.
One question concerning the narrow exotics. The question is concerning the terminology, because you wrote they are moleculous. Strictly speaking, in a moleculus, you can separate the two elements, but you cannot move one proton or one hadron from one to another unless you have fusion, nuclear fusion. So at the same time, I think it could be better to say that these narrow exotic are at the same time moleculous and tetraquark or pentaquarks, but the molecular aspect is dominant because you have a small fraction, but you can have also BB or CC, so you can take one quark from one hadron and one quark from another.
Well, that's precisely the experimental question. Since you have two configurations which have the same quantum numbers, a priori they can mix. This is what you're saying, that the physical state could be a mixture of a molecule and a genuine tetraquark, right? However, if you had a significant admixture of a genuine tetraquark, the lifetime would be very short. The fact that experimentally the lifetimes are anomalously long indicates that if there is an admixture of a genuine tetraquarks, it's tiny. That's my point. Okay?
I understood what I mean, that the two hadrons are not close enough to be tetraquarks and not far enough to be simply moleculars.
No, they are far enough. You can do a calculation and they could be as far from each other like 2 or 3 Fermi. These states can be quite large. There is something called X3872. You know, there is a simple rule in quantum mechanics. Can I have the light, please? That so you can estimate the size of a bound state by combining the reduced mass and the binding energy. Okay, so the basic rule is that 1r is roughly 1 over square root of twice delta E times m, where m is the reduced mass, okay? And for X3872, the binding energy is tiny. It's less than 1 MeV. So if you take this formula on its face value, the state is huge, much larger than the deuteron.
I have a curiosity on this last slide here. You mentioned just the prediction of this tetraquark mass made by 4 Bs. So I'm wondering if you can say something more, or maybe say which kind of signature you can have.
Which
so
kind of
these
what?
4 lepton are uncorrelated, or you expect maybe 2 upsilon, something like that?
Okay, so there is a recent paper by a PhD student from CMS.
I know very well, yes.
Yeah. And we tried to get a statement official statement from CMS, and the answer that we got was...
Maybe I can comment on this.
Sorry?
I can comment a bit on this measurement. So at the moment, this is just a thesis, a PhD thesis by this Suleiman and at the moment it is not still not approved.
It's not blessed in the
It is not
technical
blessed,
sense.
but the reason is that there are probably some background sources that has not been studied.
So I can tell you what we think is going on. Interestingly enough, to have binding below 2 mesons, it never happens when you have 4 quarks of equal mass. When you have 4 equally heavy quarks, it doesn't happen. You need 2 lights and 2 heavies, then it can work out. So 4 heavy quarks, it probably doesn't work. But what can happen is that this configuration is just a bit above the mass of 2 eta b. And because eta b is maximally light, it's lighter than upsilon. So such a state, if it exists, will not be stable, but might well be narrow. And then you expect it to decay perhaps into a pair of leptons and an upsilon, and then you see the upsilon in dimuons. So that's what we think you might be seeing. And there are numbers in our paper from some time ago, a paper with Rosner and Nusinov. This is all I can say at the moment. And I think there is consensus among experts, not just us, that if you have 4 equally heavy quarks, they can never bind below threshold of 2 heavy meson, never below 2 eta b.
Thank you.
You showed before the structure of the color flux in the case of baryons and in the case of standard baryons. And what is expected the structure of color flux in the case of tetraquarks?
Okay, thank you. This is a very important point. So basically, let's compare this guy with an ordinary baryon. So let's say we have a baryon with 2 big quarks and a U quark. So a U quark, by construction, is a 3 of color. This is just a fact. So therefore, these 2 big quarks must couple, and we know that 3 times 3 can give you either a 3 bar or a 6 of color. This is the antisymmetric, this is the symmetric combination. So they are forced to combine into a 3 bar of color. They sit on top of each other. And then you ask yourself, okay, so what's going on here? This is still 3 bar of color. So this is a 3 bar of color. And if you wish, this is just like a baryon. This is a 3 bar, a 3 bar, and a 3 bar. Another way to think about it is that you combine the 2 3 bars into a 3. So then you have a 3 bar and a 3. This is what we expect that this state looks like. And these 2 light antiquarks, again, they can combine into a state of spin 0 or a state of spin 1. And this would because they are non-identical, they can do both. But it's well known that for 2 non-identical quarks, the state of spin 0 is dramatically lighter. The difference is large. Okay, the so-called good quark and bad, good diquark and bad diquark. So what you expect is then that this is a 3 of color combining with into spin 0, and this is a 3 bar of color combining into spin 1, and this is why the total 4-quark state has total spin of 1. Okay, did I answer your question?
I was interested in understanding. You showed that in the case of standard baryon, the color flux, especially so to say, is a Y-like. What is the structure of the color flux
here? There will be a Y here. There will be a Y here because this is effectively a 3-bar. Okay. So there will be a Y between 3 anti-triplets, exactly. So for all practical purposes, when you have 2 heavy quarks, they behave like an anti-triplet. Now I did answer your question. Okay.
But in case of tetraquarks made of all heavy quarks like BB, B bar, this analogy is not working anymore, right?
Exactly.
What happened in that case?
Well, there is going to be a mixing because there are several possibilities. Okay, because there is you have to diagonalize some matrix. And it turns out, when you do, that you can never go below the quark-antiquark, unlike heavy light systems. In our paper, there is the algebra for how you do this.
Other questions? Well, if not, let's thank the speaker again.
Volevo dire che la città mi piace molto e spero di ritornarsi.
Actually, a nice discovery that 4Bs, we will invite you again.